And today I'll be speaking on semantic urbanism, adapting cities for a resilient future. So, this presentation is an outcome of a collaborative project which we have been doing along with the Singapore EDA Center as specifically Future City Labs in Singapore. And these are my superstars collaborators. Most of them are in Singapore, so unfortunately they couldn't take it to the workshop. But some of us are here. So whatever I'm going to present now will be a collaborative effort, and everyone shares the subject as we on that. So before I dive deep into the talk, I want to just give a brief executive summary. That I am what is the talk into three simple chunks. The first one is we will try to introduce what semantic urbanism is. How can you improve the privacy planning and urban design? Followed by that was the theory part of it. So now I also want to showcase that we can apply it in the practical world. So we will produce or present two papers, which is adaptable infrastructure and the smart lane management system. So adaptable infrastructure is about how we can adapt the kind of infrastructure which are rigid and passive and can we make them smarter. And the smart lane management system is about how, because the traffic is changing, it's a very dynamic thing, it's a tough thing to solve, and the future autonomous vehicle are going to come in the next few years. And how can we make them coexist with the current human driven vehicle? Alright. So as you can see here, the current system, I put a word partially efficient. I did not want to say efficient over infrastructure, so I put it Xcode. But the whole point is that the infrastructure are being designed for that specific time period. They have some leeway at a threshold of plus minus 20% that you can accumulate the future traffic and the change in the demographic and stuff. But more or less, they are very monolithic and they are rigid. So one example which we see here is a street layout. In this, what we see is that there are strict layout lays. Some of them are given to the bike lane, some of them are given to the vehicular traffic like cars and motor vehicle, and some of them are given for pedestrian. So this looks very nice, and this is a luxury in current days and age. Right? Not all part of the world has so much space. So even in this, let's say in after 10 years down the line, the dynamic of the car changes. It's no longer individual, it's autonomous. Will this say structure evolve or adapt to that situation? So that's our first contribution. Second is due to the sustainability and the mobility right? Lots of people have started walking to their work, have started banking and using the existing infrastructure. So what we see here is a bike lane is co-shared with a pedestrian, and this seems to be a bit tight. I mean, when I'm walking here, I continuously worry that if some bike from behind will pick me or not. So I'm not very like comfort. No, I'm not very comfortable walking in this space. So this is the second motivation that we currently have. This infrastructure can be adapted without asking for more space. There's a key part there. And finally, as I always open the traffic complexity is going to become very big and at 30 years. Thorough vehicles are going to come on. It was said that it will come by now. It hasn't come yet. But at least the similar autonomous vehicle act on level 3 at all. So for those, traffic can be incorporate them with the current human driven vehicle, which is let's say level 1 information. All right. So let's zoom out a little bit. So we talk about the motivation and the problem, but let's keep a little bit about cities because this is our system, right? This is the city are like a complex dynamic system, which has very dimensional, like is lots of features are there. So as I already said, let's say you plan some part of the city, a block or a traffic infrastructure at one part of the city. Let's say that you see a river in between. Let's say I make something somewhere around the bank of the river. And now I have connected two sides of the river with a bridge. All of a sudden, there is a influx of more traffic. So can that and that the centrality of that particular bridge or the edges of the street network next to it becomes really high? Will that edge accommodate it? So my point is that scenario is very dynamic, and that leads to a paradox. And the paradox is that we are trying to simultaneously understand the city and also design the city, and which is not an easy task to do. So it's so now. So what we thought about it is that we can make this a lifelong learning process, and for anything to learn lifelong, it has to be not savvy, not passive. It has to be very dynamic and adaptive. So that's the whole key thing which I'm trying to stress a lot in this talk. And Oscar, this also took is it which can improve this, or how can we take the current design process and make it more efficient for future. All right. So that was the Stewart. So then let's go to the fundamental elements of urban plan. So in urban finally we use urban elements. So urban elements in short can be AU, right? So it can be on the left hand side. There are some definitions of the urban elements. It can be a made, it can be a city block, it can be a shopping mall, it can be a street network, it can be a dust day, it can be anything. So the whole thing is urban element, and as you see on the right hand side, it's a solution, right? So you can go to a cafe or a bar, there is a ready-made solution for you, it is already be provided. So it is a solution, right? But urban elements can also be a metric for the solution. So you have plenty of option on the right hand side, and you can build your own poke bowl, or you can list synthesize. So it gives you the potential to have a conversation with the urban planning. So urban element is a tool, a method, and an entity which helps you discuss a problem and use it to solve it in terms of our time. So the improvement, not the improvement, but the next step, if you want to focus more, is on the semantic of it. Right? So it is a slight change on your own end. So in this, how we do it. So the word semantic is highlighted here, and by semantic, I just mean that we take an urban element, we make it smart, and we make it adaptive. And how do you do it is, you do it by informing it using data, uh, urban science, and the real world situations. And the main part on this is the semantic urban element can be treated both as a process and an outcome. The process is a method in which you try to learn about the system and continuously make it more efficient. And the outcome of that is that once the system is developed, it becomes the outcome. So on the picture, you see a bus stop. It's a smart bus stop. But if you consider it as a urban element, it would be a normal bus stop. Now, how can we create a normal bus stop and give a semantic and a smart bus stop? So basically, it has the information on which bus actually is going to come next, how many people are queuing up in the bus stop. It can also send the request signal to the current habit of that, okay, the bus is behind you, please clear the way. We don't have public transport ahead delay. And plus, it can also send all kinds of information. So this is what I meant. Then we take an urban element, which is just a bus stop, and we make it smart by using semantics. And and how do we so there's this certain feature of the semantic urban elements. Some of them are mentioned here. So they have to be tangible. By tangible, I mean they're not like an idea or, or something virtual. It has to be tangible, physical, like a building or a bus stop or a crash stand or a traffic light. It also has to be in its context. By context, I mean that it has to be measured using the place where it is located, the time, and its behavior, followed by human centric. Everything we are trying to do here has to be human centered, like keeping human at the center of mind and in focus. Because at the end, it's us who's consuming it, right? So it needs to be very efficient for choose. And finally, it has to be at multi level, which means that you can combine smaller semantic over elements into a bigger chunk. So you can mix and make it at the multi level. Alright, so now I want to summarize all of them as the semantic urbanism. So by semantic urbanism, it's a data-driven framework which links the physical entity with its virtual entity. And in the process, it evolves. Here we see a rough diagram which was published in one of the paper which led the digital democracy paper. He has three components in this. One is the physical environment, which is the building. He have multiple IoT devices and other sensors which can enhance the data. Then in the virtual environment, we have the digital entity of it, and this is the place where we are trying to put semantic objects here. So in this log we'll have authority, knowledge of, and the all kinds of causal relationship and this citizen and data exchange from the citizens. And finally, we have a third block, which is the stakeholder. The stakeholders leave out only the government and policymakers. It should also account for citizens, which is the main part, so which increases the transparency and hopefully it will make it more realistic because human beings are involved in it. So this is adopting book, which more or less describes what semantic urbanism is. So now, after this story, I will like to go ahead and discuss two papers because we spoke. I spoke a little bit about semantic urbanism, and that was true. But can we prove that okay, whatever we are talking can be taken to the real world and made it more practical? So these couple of papers is our attempt to showcase that it has potential and it can work. So we will discuss that. So the first one which I want to discuss briefly here is the cooperative adaptable use. So this is specifically with respect to on traffic. So in this, what we are doing is let's go ahead and see some problems which we are facing. So what you see in this picture is there is a cyclist squeezing himself on a very tiny path, and it's not a very comfortable ride. And on the right hand side, you see how vulnerable the people are when walking on the road, and the bridges they are crossing like a crossroad. It is like they're continuously about the phone, they click and whatnot. And finally, it is very congested, and so I mean, it is the space has to be equation but on the traffic type. It need not take everything from pedestrian and cyclists and give everything to the vehicles. So the point is, this is an existing street structure, right? And this is a luxury you have. It is if you have plenty of space, you can properly divide the space. But traffic, motor vehicle, pedestrian, and for cyclists. But not all street or cities have so much luxury of space. So how can we do that? So our motivation was this: the Golden Gate Bridge zipper. I'm not sure if everyone has seen this. If you have seen it, you will be really amazed by the thing. And it was implemented almost like a year ago. In this, there is a zipper like a bus, which is trying to adjust the lanes. It has the same 3 by 3. 3 lane goes into the San Francisco, 3 lane comes out of the San Francisco. So what this thing the Zumba is doing is that in the morning rush hour, when it's 8 a.m. to 1 and 8 a.m. to 10 a.m., it is hitting one lane from the other side, from the right hand side, and bring it towards the other side, which means that it is now making 4 and 2 lane structure. So because in the morning there will be a lot of traffic which will be going towards Central Bitcoin. And even rush hours, the world changes. So it's just a lane to the other side. So that the traffic outside of San Francisco is also easily there and they go without congestion. So he took that logic and tried to implement it in a record. So this is a multi-agent reinforcement learning agent. In this, we won't go much in detail, but very briefly, what is happening is that we have taken an example of a crossword which has, let's say, 4 streets and it has 8 edges. So let's consider one edge. So in this one edge, we have 3 lanes. One is for the motor vehicle, the other one is for the cyclist lane, and the last one is for the pedestrian. And how do we try to solve this problem? So remember, we were talking about adaptable infrastructure. This is adaptable streets. In this, what we are trying, our focus is that we try to adjust the same space, which is 3 lane space, which is close to 16 point some meters. Can we just take some space from each lane based on the traffic density and the mixed use case. So we have 3 agents, agent 0, 1, and 2. The goal of agent 0 is to assign how much space it should give to a motor vehicle, like for a car. And this and agent 1 has a similar role, but its goal is to learn how much space it should assign to a side pairs. And agent 2 has a very different goal. This agent 2 role is to make sure, because remember we saw cyclists and pedestrians sharing the space. So agent 2 does is that should we share the space or should we not share the space? There are multiple research which shows that if the density of both pedestrian and car and cyclists increases, sharing the space can lead to discomfort. Like there will be a conflict induced by a fast moving cycle when you front of you. So is it sensible to share the space during that time? So this agent too has a goal to learn when not to share the space. So this is what we are doing here. This is a rough architecture. So we won't go in detail, but I just wanted to highlight the top what we use in Sumo. It is a traffic simulator for manipulating and learning any model. Below is a reinforcement learning framework. It is in the 1T agent framework, so we have field agents and they are cooperating among each other. And the action space is basically agent 0 has to assign a space between 3.2 meters, and they did have the rough dimension, and similar for agent 1 and agent 2. And the reward which we are trying for the agent to learn is that it should minimize the average density for all molecule type. And it should also give strong penalization if it generates pedestrian and a cyclist lane which are quite narrow. And the incentivize it to co-share when the rest is slow. So we have these three systems in Latin, and based on that, the agent tries to learn. So very briefly, we go through the results here. So what do we see here is that count is alone cooperative or adaptive behaviors, and we are compared it with the static FT. Static FT is the current status quo, like the face structure. They're not changing. Every day has the same bit. So in this we also is that we have reduce the waiting time for the overall average, and also the reduce the queue length compared to all other options. And once I will show you the next, I will see how by how much. Here we also, so this is the same result shown above, and level of service is something which is very common, well-known measure for measuring the comfort of pedestrian inside is. So the lower value levels of service, the material. A level of service that means how comfortable you are in walking, and if the street space has made it properly. And the last crop which you see here is the place where the pedestrian and the cyclist lane are being shared, one not shared. So what we observe here is in our model, during the early morning time till let's say 8 a.m., the lanes are shared. Maybe because everyone is going towards the office and the density is still low. But during the rush hour time, people are like in the during the lunch time and the 6 p.m. time, people are not so they might get high density, and the rates of the pedestrian necessities are no longer kosher because maybe of the people are, there's high density, and then it again starts sharing after the peak hour is over. This is to showcase the results for decentralized and centralized. What we also hear is let's go back to. So you saw this four rows, right? So by centralized, what we did is right, we had multi-agent for all the edges. So we have eight edges into three. So for info edges were being trained simultaneously. That was the decentralized in the centralized version. In the decentralized version, what we did is we only made one edge that had three edges here, and then we took the logic which had one edge on key edge, and we gave the same thing and shared it to the area edges. So it means that if you want to make a cityscape, you can easily expand it. So that's the difference between decentralized and centralized. And what we observe here is that the decentralized has worked way better compared to the centralized. Even the level of service in the decentralized is good. So finally, what we observe is that when we use this our adaptive system, we have reduced the waiting time by almost 48 minutes and 48%, and the results of the QA is also done by very several. And decentralized model, of course, on performs decentralized. These results are done by simulation. So, of course, to make 100% agreement with this result needs to be for the tested. Okay, so very quickly, they discuss failure. In this, what we are trying to solve is the traffic of the future. We know that autonomous vehicles are going to ground needing up now, 85 years down the line, but currently the system is about how can we kind of- they have to hold the autonomous vehicle doesn't come, but the semi-autonomous vehicle has. But the model that we see currently now in this research is that they assume that there's 100% autonomy and we're seeing what there's nothing in between. So we wanted to try to solve that problem. So, but the challenges are similar, like the lanes are assigned to autonomous vehicle, which is the priority lane, but it is empty because it's not autonomous vehicle. There are few of them, but it more or less the space is unoccupied. And then the other traffic, human driven traffic, are using the tight lanes, and I mean they just can't use this space which is already there. So this is what we do. We consider these three different autonomous vehicle, like level 4, 5, the pre-autonomy, the semi-autonomous vehicle, and the human vehicle. And due to the brevity of time, I will skip this item. And this is of simple failure logic which can be understood here very clearly. So these are three logic which we want our agent to learn. The first one is the right of way. So what we see here is that we have this is our autonomous vehicle, and it has a clearing distance. So this number 9, which is the agent which you are trying to learn, has to give way. So this is so the goal is if a autonomous vehicle is behind you, you should move out of the way. And we are trying to make the semi our religion to learn how to step out of the way. The second learning which it needs is that if you are standing at the intersection, there is the area, please move out of the lane as well. So these are the things which you want our agent to do. And then the safe lane change. So do not come into the priority lane if there is already an autonomous vehicle behind you and there is a less than a threshold. Simply this is it. So very quickly when we see the results, we see that the best result is happening when the semi-autonomous vehicle is in the percentage of 30 to 50% of the overall traffic, along with the CAD penetration rate is 5%. Why? And anything else does not work. So we can. So okay. So the one thing which has happened from this work is that it has produced results which can be clearly translated into policy. We can focus on only these two, which is like currently people are saying that since there is a autonomous vehicle and it cannot coexist with the human driven vehicle, how should you make the system? So currently they are putting a priority lane and it is only dedicated to the autonomous vehicle. But what our research showcase is that if the priority with the autonomous vehicle are not in the range of 30 to 40% of the overall traffic, that lane will be unoccupied. So do not in the end implement a system which we are proposing, which is they push the link between the semi-autonomous vehicle and the autonomous vehicle. And also, this also essentially have produced a results for varying the percentage of the penetration of both autonomous, semi-autonomous, and human-driven from 0 to 100%. This tells us that our method can continuously showcase that you can have a prediction of your continuously monitor the traffic performance and you can adjust which lane software to provide. Either it should be the IT lane or it should be like a dummy activities. So the contribution for this outbook is that we have provided nuanced information, which means that it cannot be binary, like either fully calculative or not calculative. It can be in between. Also, it gives urban planner and a way to understand how to allocate the range space and to share them together. And finally, it is more fair use of the system because there are many people like me who I do not want to use autonomous vehicle. I do not trust it. But I will say do a human driving vehicle. And if you take the space from me and you to autonomous vehicle, what happens? So this letter also should have any failure assist for Jukes. So when we talk the applicable, which is the setting must use the evolve. It should be human centric. Features of the coordinated speed collaboration, the setting engagement. And with that, I would like to thank you and now get the power push.